Hello, everyone. So since today we had a lot of great and super advanced application of liquid crystals, and so I decided to prepare something more on the how-to side, so that we can actually look together a little bit on how to prepare hands-on in a way this kind of materials. So first of all, what are photomobile polymers? PMPs are intended as plastic films, basically, that can be deformed by using an impinging light, and you can modulate this deformation with the intensity of light, polarization, and wavelength. In literature, you can find a lot of this kind of material. They're usually based on the light-induced chemical isomerization of azobenzene, liquid crystal base that are the most common, are the one that we are going to talk about today. The Marangoni effects, these exploit the surface tension gradient, thermically or chemically induced, or the bilayer PMP. These usually are the most simple one. They basically exploit the different expansion coefficient between two layers. You can do it at home, basically. It's very easy. If you take a piece of filter paper and you put it in a, the kind of filter, ceramic filter, the one for vacuum, and you filter off a solution with some polymer with graphite, you will get this kind of material. So it's a bi-layer, and the two layers have different coefficient, expansion coefficient. So today we're going to talk about this kind of material. So first of all, what is azobenzene? We heard about it today, and is a molecule basically that is able to isomerize when irradiated with the UV light. It is a molecule that is in his most stable state, so low energy state isn't transformed, as you see on the left part of the slide. When is excited with the UV light, absorb this energy, it can go to this cheese form. Interestingly, if you leave it in dark, or you heat it up, or you use visible light, you can convert directly this cheese form in trans. Instead, what are liquid crystals? These molecules can be defined as an intermediate between a crystalline solid and an amorphous liquid with an ordered arrangement of molecular orientation, and furthermore, they have anisotropic mechanical, electromagnetic, and optical properties. As you know, there are different kinds of liquid crystal. Most known and studied are in function of their phases, nematic, osmotic, and cholesteric molecules. Nematic are molecules that arrange parallel to each other, but they are able to move in all directions with the free rotation. And usually there is an average direction that is called director N that we can control to give to this material, this molecule, a long range organization. Osmotics, they have not, they're similar, but they don't have only this kind of orientational ordering, but they have a positional ordering too. In fact, they form layer, packed layer, and they are more similar in this way, more similar to a crystalline than to a liquid. The cholesteric can be seen as liquid crystalline nematic state, but because they can rotate in their plane, but at the same time, each plane, each layer is rotated by a certain angle. An important thing to remember about liquid crystal, they are thermotropic. So in function of the temperature, they can change their state, and of course, in function of the pressure too. So if you want to characterize, for example, the properties, this is an important thing to keep in mind. For example, go a high temperature to keep your mixture, whatever mixture is of liquid crystal, in an isotropic state. It means that the Brownian motion will win against the interaction between the molecules that are in the mix. When you start to cool it down, you will arrive at a critical temperature where instead the interaction between the molecule will win against the Brownian motion and start, for example, to go into a nematic phase where there is mainly an orientational ordering. If you continue to cool down, if it's the case, of course, of your mixture, you will arrive to a smective phase where there will be a positional ordering too. Of course, in function of temperature and pressure, you can modulate this kind of states. Anyway, of all these kind of liquid crystals, so these liquid crystals basically are the most used for the production of PMPs because they are actually very performing in terms you can use as wavelengths, condition, polarization sustains of the light and change their properties. And they, as Professor Zeng showed, they have an incredible edging angle, so they are very you can do a lot of things. And of course, one of the most important things, they are commercially available. So you can buy, for example, from BIMCO in the US or in last years even in Europe. So it's easier to have industrial approach, for example. So if you're thinking about an application, it's easier to approach to this kind of material than the other kind of PMPs. So here is an example of liquid crystal-based monomers. This in particular is the mixture that was invented by Professor Zeng. We started to use these two in our project because it's actually very flexible, and as compared to other compositions, you see that there is just 6% of azobenzene. So this is actually helpful in preparing the PMP itself because of some special properties of this molecule. One suggestion is of course, go towards the use of nematic liquid crystal for PMPs because they are most common, most sometimes more the one that are more simple to use. But one important thing to remember is to be able to control the orientational order. Okay, this is a schematic that we use to explain a little bit how we do the polymers. We will come back to this, but this is here because the first thing to do to have control on the orientational order is to prepare your cells, rabbit cells, to give the director end that you want to your materials. This because even though, let's imagine that you know where your mixture, and you know the temperature in which your material will be nematic. If you just are on without any control on the orientational order, you will have the situation that you have on the left. So the liquid crystal will form pockets of ordered liquid crystal. So some will be oriented in a direction and some in another. Instead, if you want to have a long range order, you will have to have you want to have a monodomain. So you need to have something to have this control over orientational order. For example, as we say, have rabbit cells. So when you polymerize your material, you're going to freeze the order that you so difficultly created. How to do that? One example is the rubbing. As we were saying, usually what you do, you use a satin cloth and you rub coated glass slides. You can use a wooden stick, as you see on your left, or a 3D printer, as you see on the right. I mean, of course, the best thing is to have complete control. So 3D printer would be better, or something that you control X and Y axis, for example. So after you got, of course, your rubbing, you will have to prepare your rabbit cells, and the best thing to do, of course, is to try to optimize. I was saying your the preparation of your cell. For example, test various polymers for your coating, because maybe different polymers will interact differently with different liquid crystals. Check the layer thickness. For us, for example, for mixture, we're using the layer of elvamide that we coat on the glass. Work best with when it's 200 nanometer. In fact, this is an example. You see these images on the left. on the left, you see a PMP prepared when the layer is just 25 nanometer, and as you see, even is irradiated, the PMP is not moving forward, it's not bending. Actually, you can see here, but actually had a torsion towards us, towards the camera. Instead, when the thickness is high enough, you see that the film bend towards the, in this case, toward the laser, can go, of course, to self-vibration. Another important element is, of course, to know the thermal properties of your material. Each mixture will be different in terms of especially in terms of thermal properties. One of the first things is to understand where is the isotropic temperature. So you can go to isotropic temperature and start to cool down to organize your material. One of the easiest approach is to use DSC, of course. And these are two as an example of DSC. The one on the right is of a cross-linker, azobenzene cross-linker, and you can easily see that are present two melting points. And this is actually pretty normal for liquid crystal. In fact, the first melting point is the passage between a crystalline to a nematic phase, and then the passage to an isotropic phase. More complicated becomes when you use a mixture. On the left is a mixture of both 100% azobenzene, cross-linker, and linear polymer, let's say. But you see, let's see if I can put a pointer. Yes, you see that between the two melting points, you can't really see where as here where the nematic range is, because in this kind of mixture, the nematic range is so short that you need another approach to find out. One example that can help, one approach that can help to solve this problem is to use the order parameter. There are various ways to calculate your parameter. We use this approach. I'll talk about that later. So just a few words, what is the order parameter? Is a qualitative and quantitative, depend on the conditions of your experiment, parameter. Is a parameter that can help you to understand the orientational order of your mixture. So it's an empiric approach. So whatever, in this case, we are using the transmission, as you see. So in the condition, whatever you use, that will help you to understand what is the best condition to have anematic or the nematic phase, so the best order possible. Usually, with our approach that we're going to explain, you're going to have a range between 0.3 and 0.7. 1 will be the perfect condition. Of course, that's never happened. That will never happen. And the equation that you see is the empiric equation that will help you to calculate this parameter. Here, there are a few examples of this kind of experiment, but of course, as I said, different condition will give you different results, a quantitative or a qualitative result. On the right, far end, right, you will see that the range of the order parameter is between 0.3 and 0.7. It means that in this case we had a good condition. It means that the wavelength, as you see, is 457, is a wavelength that is absorbed, about 80% of the wavelength is absorbed by the mixture, so give a good absorption. And then, of course, for example, you will have better condition in terms of how the experiment is performed. For example, the power meter has to be, if it's possible, to be attached as much as possible to the heating device so that there is no dispersion of light. So, but what this scheme means? So we have, of course, a laser. In this case is represented as 633 nanometer, but can be any wavelength of your choice that has a polarization, in this case, parallel to the table. Your cell, infiltrated with the monomer without, of course, any kind of initiator, will be inside the heating device that has a quartz window that will let pass the laser. So your cell is in between, and so basically what you're going to do, you're going to measure the transmission starting from isotropic temperature going down, which then your monomer becomes crystalline again. And it's important that your cell will have to be parallel with the rubbing, parallel or perpendicular to the table. So this way, you're going to measure the transmission low light in this condition, calculate the absorbance from that, and then put in the equation. You will have, of course, your order parameter. It's a very practical approach, actually. What you see instead on the left, then, is a graph that are using less, not in optimal condition. In fact, as you see, the order parameter is not is 0.05 is very low. So in this case, it is more like a qualitative approach. So you're going to have a range of temperatures. So in this case, 532, for example, is comprised between 82 and 84 degrees. So you need another approach to understand what's the temperature in that case that will be the best temperature for keep your liquid crystal in nematic conditions. One approach to solve this problem is the one that you see here on the bottom. The main difference is that we put another polarizer here that is perpendicular to the table. So we have the laser that is parallel to the table and the polarizer that is perpendicular. Of course, if the cell inside the heating device is parallel or perpendicular to the table, we're going to have a minimum of transmission, because the light will be or cancelled by the half-wave plate or by the cell, in case we are, of course, in a nematic condition, right? Then if you put the cell at 45 degrees, what's going to happen is that the parallel light will be rotated at 45 degrees and then rotated again at by the polarizer. So this means that if the temperature is nematic and the cell behaves as a polarizer, we're going to have a maximum peak. And this will help you to understand where is the nematic temperature. And I have some graph like that, for example. So you see that we have various places where there is a maximum between the orthogonal, tilted, and parallel signal, but we have the most high signal is at 88 degrees. So even though in that case we had a range between certain temperature, in this case was between 84 and 89, with this approach we found that 88 was the only, in that case 88 in 87, the temperature in which the liquid crystal will have the best order, because behaved as a polarizer. So after, at this point, of course, you prepare your mixture with the initiator and you polymerize it. And you have different possibility to characterize it, to understand it actually if your material is good. Of course, you can let it move and see if it moves, or to see if it's able to rotate the polarized light. So after the polymerization, so you be sure in that case that even you polymerize, you applied an energy to it, the liquid crystals are still in a nematic condition. And you will see something like that. So you see on the left, the film when that is tilted of 45 degrees as compared to the polarized light. Instead, on the right, you see when the film is actually parallel to the polarized light, so that we have the minimum transmitted. Another example, useful example, when you don't know the mixture, you want to be sure that the polymer, you choose the right temperature, is to use X-ray crystallography. You see on the left, this is the crystallinity of monomers, on the right of the polymer. So you see that there is, on the right you have an amorphous phase, so yes, it's polymerized, but this gives another information. Is not osmotic phase. So osmotic phase usually is lower in temperature than nematic. So if you have polymerized at the osmotic phase, you will have sharp peaks that will indicate the layer formation and actually not only not orientational but the positional ordering of the liquid crystals in your PMP. Yes, of course, the use of in this case, in this kind of material, the use of spectrophotometer is a must. You see two different composition here on the left. This is an experiment to show the absorbance, transmittance, and reflectance of the PMPs. So if you are using light to do something with your material, you want to know what are the best conditions to use these materials. You see on the left, we have an absorbance, for example, up to 500 nanometers. And this says that, or here on the right, the best be 405 or up to 457. That is just like 70%. This is interesting to know because let's imagine that you are converting light to mechanical energy. You know that you're not giving all the possible energy. So even though maybe that behavior, a different wavelength would be lower, is not a problem of the polymerization or the condition of polymerization, but of how the PMP itself is behaving. This is another experiment that you can do with the spectrophotometer. So if you, for example, you want to know how your adsorbenzene is absorbing in the matrix that you prepared. So you prepare a PMP without adsorbenzene and then use it as a background reference. And you will have, in this case, just the absorbance of the adsorbenzene inside the matrix. You see on the left, this is 457 that is both absorbed by trans and cis. In fact, you see that we don't have much difference in terms of shape, let's say like that, of the absorbance curve. This is because the average of conversion is not in favor of the cis molecule with this wavelength. In case instead of an UV lamp that goes to 400 nanometers, you have actually, you see there is this shoulder forming that indicates this conversion. Here's an example of optical table setup. This is an old setup that we were using before. So you see you have a laser source. In this laser source, you can't regulate the power. So a good choice would be a neutral filter that help to modulate the power, and half-wave plate to rotate the polarization, a chopper to have impulse on and off, and of course the sample stage. And here there is a lens to focus your light. With this kind of setup, for example, you could do this kind of characterization for us have been actually very, very useful. I'm showing you this in particular because this shows two different PMP, they're exact same condition of polymerization, of injection, so the same cell, so same kind of rubbing, etc. But the temperature is different. So one is polymerized at nematic temperature, and one is 10 degrees higher. And you see that at the same power density, even though it's the same mixture, we have a complete different ability to convert light into mechanical energy. This is speed actually, so this is in meter per second. So last but not least, I want to show you a few videos that we're doing. So this is actually this kind of material that I showed this mixture, but doped with some nanoparticles, giving to it the ability to absorb red light and stimulate the actually self-vibration with red light. This is all the same. This is an example of different absorbance of this material at different wavelengths. So we have 132, and then of course the ones that are more, the stimulation is much higher with 457 and 405 nanometer. And okay, this is another kind of material. This is material doped with zinc oxide nanoparticles that is crammed with nanoparticles. Inside is full of 6% of nanoparticles, a lot. So from transparent becomes opaque. I'm showing you this as an example that if you optimize your process from start, you're gonna have great results. Because these, it actually shouldn't vibrate because nanoparticle goes out of the surface of the material, but actually it goes of course, it goes towards I don't know if you can see it from here, but it's vibrating, I assure you. Well, thank you for your attention. This is our group, and we work at CNR. If any of you have more questions and it's interesting, of course, can contact me or any of the group, and we answer all your questions.